Okay, so in this lesson we're going to go through the questions that you did last lesson. So, question 1. Some students measure the level of radiation from a radioactive source during the same lesson each week over a period of 6 weeks, and here are the results, and you're plotting a graph. When you do that, the first thing I want to do is look at the scale and work out what 1 square is worth. So if that's 20, this is 10, so each square is equal to 2 counts per minute of radiation. So as soon as I've worked that out, it's pretty quick to plot your graph. You'll get 6 points correctly plotted will get you a mark. All 7 correctly plotted will get you another second mark, but only within half a square. So the first one at the start is 66, so it's 246. Second one 44, 24. Time 2 is 34, so 24. Times 3 is 29, so that's halfway between 28 and 30. Times 4 is 16, so 10, 2, 4, 6, 16. Times 5 is 12, so 1 square above 10. And times 6 is 8, 2, 4, 6, 8. So that'll give me the 2 marks. And then for the third mark, I'm going to do a line of best fit, which I suspect I'm going to make a mess of. But the point here is to notice that we've got a curve, but this one here is an anomaly. So I need to make sure I miss that out of my line of best fit. Went a bit rubbish at the end, but you see my point. I could then just rub that out and improve it. But this one is not going to sit on the line of best fit for my final mark. So the next question is, what overall pattern is there in the student results? And that's worth 3 marks. So for my first mark, I would say that radiation decreases with time. That's my simple first mark. Then for the next mark, I'm going to describe that pattern a little bit more closely. So I'm going to say that it's decreasing rapidly at first, and then it will slow down. So I'll say it's rapidly at first and then slows down. There's my second mark. And for a third mark, I'm going to say something about the half-life. And if I look, so 66, half of 66, 38, so that's 2. So then 2 weeks, roughly speaking, it's halved. So I've got a half-life for about 2 weeks, or you could say that it's that the count rate is decreasing roughly every 2 weeks for that third mark. So next question. The diagrams below are 3 atoms A, B and C. I've got my 3 atoms A, B and C. I'll just take a quick look at the diagrams before I answer the question. I notice that I've got my protons and neutrons, but I don't know which is which, but I do know what my electrons are. I'm told they're atoms, so I know there's the same number of protons and electrons in an atom. So still none the wiser on this one. I've got 4 and 4 and 4, 4 and 3 and 3. So these ones clearly my protons, these ones my neutrons, and these are my electrons. So it's always worth just spending a little bit of time on the diagram before you answer the question. It can really help you to not get confused once you started to read the question. So 2 of the atoms are from the same element. Which of A, B and C is an atom from a different element? So different element has a different number of protons, and therefore of an atom electrons as well. So therefore it's clearly B, because it has got a different number of electrons or protons. Either will get you that mark. 2 of them isotopes. Which 2 are isotopes? So isotopes have a different number of neutrons but the same number of protons. So A and C are isotopes. They've got the same number of protons, or you could say electrons in this case, or you could say a different number of neutrons as well for my third mark. So question 3, Sam and Chris are arguing about alpha and gamma radiation. Sam says alpha radiation is more dangerous. Chris agrees. He thinks gamma is more dangerous. Chris disagrees, sorry, he thinks gamma is more dangerous. What do you think? Well, alpha and gamma are dangerous for different reasons, aren't they? So, how many marks is this worth? Let's have a look. So it's worth 4 marks. So if I need 4 marks, I'm going to need to do 2 points about each. So therefore I can say that alpha is more dangerous because it's more penetrating. Sorry, why did I say alpha there? On my notes here I've written gamma and I just said alpha. Gamma is more dangerous because it's more penetrating, I could say, and therefore it reaches the cells through the skin. And then for alpha, I'd say alpha, however, is more ionizing, or more damage is caused, or you could actually just mention cancer specifically there. And the reason for that is because it is a bigger, it has more mass, it has more charge. But then as a second point, you could point out, however, that's only if it gets inside the body that it can cause that damage. Okay, next part. So cancer cells in a particular organ of the body can be killed by injecting a radioactive substance. So it's injecting a radioactive substance which is absorbed by that organ specifically. What other features must the radioactive substance have so that it's suitable for the job? So if I'm wanting to kill a cell, I want to use alpha so that it's ionizing, so that it will actually damage the cells. But the other feature I want its half-life to be long enough to kill the cells, but no longer than that. You don't want to just say a short half-life, because if you just say a short half-life, you're implying that it could have a really short half-life then, and then it wouldn't be long enough to actually kill the cells, because it would have gone before it even got to the organ. So be specific on those sorts of questions, that the half-life is just long enough to kill the cells, but not longer, not significantly longer than that. Radon's a radioactive gas. It has a half-life of 3.6 days. It often seeps into buildings from the ground. Estimate how long it takes for 99% of the sample of radon gas to decay. So if I start with 100%, how many half-lives does it take to get to 99%? So half of 100 is 50. Goodness for about pens. Half of 50 is 25. So I'm counting how many half-lives I've done. Half of 25 is 12.5, half of 12.5 is 6.25, half of 6.25 is 3.125, half of 3.125 is 1.5625, so I'm nearly there. I've still got only over 1% left, and half of 1.5625 is 0.78. So it's somewhere between 6 and 7 half-lives. So 6 half-lives would be 6 times 3.6, which is 21.6, and 7 half-lives is 25.2. So anything in between those two values will get you the mark, but those two specific values obviously wouldn't get you the mark. So therefore, even if you put 21.7, you get the mark. So it's anything in between those two values will get the mark. So your first mark is for showing a way of counting up how many half-lives it is, and your second mark then is for any number between these two numbers. Atoms are made up of 3 types of particles called protons, neutrons, and electrons. Complete the table. So a neutron has a relative mass of 1 but no charge. An electron. Now, we're starting to be really specific about this now. We don't want to just be putting 0 in it at this stage. We want to start saying things like very small, negligible. If you want to be really specific, you can start doing fractions of masses. But 0 is not always going to get you the mark, so I want you to really start using the correct terminology now. minus 1 is the relative charge. Diagram below shows the paths of two alpha particles A and B into and out of a thin piece of metal foil. We know this experiment, we recognise it as the way that the work that Rutherford did that led to the nuclear model of the atom. So I'm spending a little bit of time in my head just thinking over what this is telling me before I carry on to read the question. So, the paths of the outer particles depend on the forces on them in the metal. Describe the model of the atom, which is used to explain the path. So I'm describing the model of the atom. Well, the model of the atom I'm describing, therefore, is the nuclear model, as I said. So therefore it has a small positively charged nucleus. You get the mark for not even saying small, just that the nucleus is positively charged, hence that deflection. And the negative charges, or I could be quite specific here and say the electrons are in orbit or shells around that nucleus. So that's my 2 marks. In the early part of the 20th century, scientists used the plum pudding model to explain the atom. So here I've got a plum pudding model. Following the work of Rutherford and Martin, this new model came out. This is the nuclear model I just described. So I've got to do the differences between them. I'm looking for 4 marks. So I can have any 2 from. So it's one of those ones that might be easier to look at the mark scheme again because there's quite a lot of different things that we can accept here. So we're looking for any 2 pairs of answers. It's got to be clear which model you're describing. You can't just say one has this, the other has this. So we need a comparison. Nuclear model has the mass concentrated in the centre, whereas plum pudding model has the mass evenly distributed. Nuclear model has a positive charge in a small part of the atom, where there's a plum pudding model, this positive charge is spread throughout. So if I had those 2 pairs, that's my 2 marks, that's my 4 marks, sorry. Other pairs that you could have are nuclear models, electrons orbit at some distance, whereas in the plum pudding model they're embedded within the positive charge. Or the nuclear model is mainly empty space, whereas the plum pudding model is a solid mass. So I've got 4 different pairs there, but you only need 2 pairs to get the 4 marks. Okay. When an atom of thorium-232 decays, an alpha particle is emitted from the nucleus, an atom of radium is left, an alpha particle is 2 protons and 2 neutrons. We can represent it like this. Thorium-228 is radioactive as well, so another isotope of thorium. Atoms of that isotope decay by emitting an alpha particle, draw out that decay. So first I'll do my alpha particle. I could put just He in place of the alpha sign there, and that gets me 1 mark. Then I work out what the numbers are that it decays to. So take away 4224, take away 288. So that will get me my 2nd mark. 88 is the same atomic number here, so therefore finally again it's decayed to radium, will get me my other mark. So I've got, sorry, I didn't say these are individual marks for those 2 numbers, so that's 1, 2, 3, 4 marks. An atom of radium-228 decays by emitting a beta particle, and they've given you the symbol for the beta particle, and they've told you it's a neutron turning into a proton. An atom of actinium remains, and there is the decay. However, an isotope, this isotope, so of actinium, also decays by beta radiation, and we have to write out the decay for that. So the first thing I'll do is my beta particle for my 1st mark, or I could do obviously the beta symbol. So that gets my 1st mark. I then will do my calculations, so therefore the mass hasn't changed, but I have gained a proton because that neutron turned into a proton. And then it says here that it's an isotope of thorium that's left behind. So those are my 4 marks there. Thorium-232 eventually decays to lead, and here are the steps in the process. So I've got the number of nucleons or protons and neutrons there, the mass, and this is showing that, and these are the number of protons. So in this decay here, the mass is decreasing. The number of, it's not necessarily the mass, is it? Yes, it is, sorry, yeah, of course. Number of nucleons, protons and neutrons. So therefore, here the mass has decreased, as has the number of protons. Here, the number of protons is increasing, but there's no change in the mass. So therefore, what sort of decay is this? Well, if the mass is decreasing and the number of protons is decreasing, that must be alpha decay. These must be beta. This is all alpha decay. This is beta. This is alpha decay. So during the decay from A to B, loss of mass and loss of protons, that's an alpha particle that's been emitted. B to C, however, I have increased the number of protons, neutrons have turned into protons, no change in mass, so that's beta decay. E to F, loss of mass and loss of protons, alpha decay. I to J, no loss of mass, increased number of protons, beta decay. Only 2 marks, so therefore to get 2 marks you have to get them all correct. If you only get 3 out of the 4 correct, you'd only get 1 mark. 2 out of 4 would also get you 1 mark. 1 out of the 4 won't get you any marks at all. Okay, so the table shows how long it takes for half of the atoms of each isotope to decay. So let's have a look at this then. So to go for A to decay takes, for half of A to decay, takes 1 billion years. For B, 7 years, 6 years, 2 years, 4 years, 1 minute, 0.4 seconds, 10 hours, 1 hour, and finally J, 0.3 milliseconds. Lead, as we know, is the stable isotope, so therefore it will not decay at all. Okay, so I found a rock sample and it contains a lot of thorium-232, which is A, and even more of the lead-208, which is the final stable isotope. Hardly any atoms of any of the other isotopes are there. Why? Well, thorium-232 takes billions of years to decay. So the reason why I've got a lot of thorium-232 is because thorium-232 takes billions of years to halve in number. So I wouldn't expect that all of a significant amount of that to have decayed. It takes too long. It takes a long time to decay. Lead, I would expect there to be a lot of lead-208 only if actually billions of years have passed. So billions of years must have passed for there to be lead-208 present. So we know that this piece of rock is billions of years old, but it would take many billions of years for it to actually halve the amount of thorium, so there'll still be a lot of that there. You could also point out that lead-208 is stable. So therefore once it's decayed to lead-208, it's not going to decay further. So therefore once, billions of years have passed and we've got lead-208, sorry, the cat's just walking across. The lead-208 is then stable, and so therefore that will be there. So the only thing that I haven't mentioned then, so I've mentioned the thorium and explained why there's quite a lot of that there. I've mentioned you can't be here, I'm sorry. I've mentioned the lead, and why that's there. The only thing I haven't mentioned is the fact that there's hardly any of any other isotopes, but if you look, they've got relatively very short half-lives, so therefore hardly any of the others due to their relatively short half-lives compared to the thorium, so therefore you wouldn't expect to be much of those present at any one time. Uranium atoms don't always have the same number of neutrons. What are atoms of the same element which was given? Now, this is an easy one, isn't it? So isotopes. By emitting alpha particles, an atom of uranium-235 decays into an atom of thorium. I don't think I went right, did it? The alpha particle, the same as a helium nucleus, we do like this. Complete the equation. So I've lost 4, so therefore I've gone down to 231. Lost a mass of 2, so it goes down to 90. There's my 2 marks. Nice and simple. This is uranium-235 being split into several pieces. The splitting is nuclear fission. They will accept just one S, but they won't accept anything that could be mistaken for fusion. Particles X are your neutrons. Uranium-235 is used as a fuel in nuclear reactors. We didn't actually cover this in lessons, did we? You need to know uranium-235, and the other one is plutonium, and it's 239 actually. Those two you need to know are the fuels, the most common fuels in nuclear reactors. Doctors sometimes need to know how much blood a patient has. They can find it out using a radioactive solution. After measuring how radioactive a small syringe of the solution is, they inject it into the patient's blood. And here's a picture of the blood circulation. So the blood is circulated through the lungs and also through some other organs. Some of the special solution will get into the cells of those organs and the kidneys, and some will get into the urine. Okay. So they wait for 30 minutes so the solution has time to become completely mixed into the blood. Then they take a syringe full of blood and measure how radioactive it is. And I'll just refer back to the fact that I just read all of that. I think you all have a tendency sometimes to skip diagrams because you think, oh yeah, no, I think I know what that diagram is about. Don't forget to read these things. They're hints that might be useful in us answering the question. So if a doctor injects 10 centimetre cubed of the solution, diluted 500 times, there must be 10 times 500, 5,000 centimetres of blood. So 10 centimetre cubed of radioactive solution gives a reading of 7,350 counts per minute. The blood only has 15 counts per minute. So I need to know how much times smaller that number is in order to find out how many times it's been diluted by in order to calculate the volume of the blood. So therefore I am saying that 15 times something, how much times smaller it is, equals 7,350. Therefore the amount of dilution there has been is 7,350 divided by 15, and that gets me 1 mark getting to that point. The answer to that sum is 490 times, and that is my 2nd mark. So if I know it's 490 times diluted, then 10 centimetres times 490 equals 4,900 for a mark, centimetres cubed for a 2nd mark. So, radiation from radioactive substances can harm my body cells. The doctor's method of estimating the blood won't be completely accurate. Why? Well, there are various reasons why, and 2 of them are given to me on this diagram, aren't they? They said some will get into the cells and some will get into the urine, and that won't be present in the blood anymore. So some will end up in cells, some will end up in urine. That's 2 of the 3 marks. Also, the radioactivity level will actually decrease because some will decay while it's in the body. The doctors use radioactive substance which loses half of its radioactivity every 6 hours. Why is that suitable? Well, the reason that's suitable is because that's actually a relatively short half-life, isn't it? So there won't be, not much will be lost or decay within the time frame of the of trying to find out how much blood they have during the procedure. But also it won't stay radioactive for too long after the test has been completed. Okay, great. That's it for this week. If you could just upload a photograph, or some of you have been doing videos where you just flick through the pages just to show me what you've done. It's great to see how well you're annotating your scripts and you're making those improvements. Well done. Good work, and I shall see you next week.